Okay. Oh, we're going back to the top here. Just got all inspired. I like being inspired. Okay. So here we are. Today we're talking about horizontal asymptotes. And I'm going to make absolutely sure, one, that I started recording, I did, and two, that my microphone is working and video, and it is. And so here we are. Here are some rational, 1, 2, 3, 4, 5 functions, rational functions. And as part of learning to analyze them, what we're going to do first is find the other kind of asymptote. We worked on vertical asymptotes yesterday. Today we're working on everything, but the intro to working on everything is to learn about horizontal asymptotes because there are, here I am, because there are 3 rules that you will need. And each one of these problems illustrates one of those rules. Okay, here's our first problem, and these are your homework problems, by the way. 3x to the third plus 2 over 2x to the third minus 3. The first rule is this, or is illustrated by this. Let's do it and then try to put it in words. When the top power, when the highest power on top and the highest power on the bottom are the same, this is what you do. You take the highest power term from the top and put it over the highest power term from the bottom. Now, because these terms are the x part of the term, the variable part, these parts are completely the same, they cancel out, don't they? Leaving you with 3 over 2. Which, as Myra pointed out yesterday, is 1.5. It is. But we leave it this way just to keep my math lab happy, but it's good to know that it's 1.5 because you're going to have to actually graph it. Okay, so this rule says that when the highest exponent on top, highest, let's stop the baby talk and let's just talk about what we really mean, the degree of the top. The degree of the numerator. When the degree, I guess I should say degrees of the numerator and denominator are the same or are equal. The horizontal asymptote, which we call HA, ha. The horizontal asymptote is the ratio of the leading coefficient of the top to the leading coefficient of the bottom. This is the leading coefficient because it's the coefficient of the highest degree term, which ought to be in front. And this is the leading coefficient of the denominator because it's the coefficient of the highest degree term, which should be in front. So it's leading. The ratio of the leading coefficient well, let's just say leading coefficients. Okay, when the degrees of the numerator and denominator are equal, the horizontal asymptote is the ratio of the leading coefficients. So the actual horizontal asymptote, because it's a horizontal line, a dashed red horizontal line, just like the vertical asymptotes are dashed red vertical lines. Well, this is a horizontal line. Y equals 3/2 is the the horizontal asymptote. Ha ha ha. Okay. So when the powers are the same on the highest powers are the same on the top and on the bottom, all you do is use the numbers in front of the highest degree terms. You form a fraction like this, and then you say y equals the fraction, and this is the equation of the horizontal asymptote. There. That's your first rule. I mean, I don't know that they're even numbered, but that's our first rule today. Next horizontal asymptote. Here we have a rational function. The numerator is x squared minus 9. The denominator is 4x to the 4th plus 5. Notice that the degree of the numerator is less than the degree of the denominator. Very important. When the degree of the numerator is less than the degree of the denominator. And that's certainly true here. 2 is less than 4. Okay? All right, when the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is are you ready? Here's the equation. Y equals 0. Automatically. So y equals 0 is the ha. You have to know where that is, though. Y equals 0 is the equation of the x-axis. That's all there is to that. Is that great? When the highest power on top is less than the highest power on the bottom, you don't even need to calculate anything. The horizontal asymptote is y equals 0, the x-axis. Now, sometimes you have the other situation, when the degree of the numerator is higher than the degree of the denominator. The degree of the denominator. You ready for this answer? When the degree of the numerator is higher than the degree of the denominator, you don't have a horizontal asymptote. You do have a different kind of asymptote. It's called oblique, but we don't learn about that in this class. So it's enough for this class to say there is no horizontal asymptote. This is perfect for flashcards. If you make flashcards for yourself and actually read them every day, you can raise your grade 2 or 3 letter grades in all your classes. Or at least one. Okay, now let's go back to this. Here again, we have the degree of the top equals the degree of the bottom. The equation of the horizontal asymptote is y equals 2/3. And that's the totality of the work that you have to put into this. And down here, the degree of the top is less than the degree of the bottom. So the equation of the horizontal asymptote is y equals 0. That is the x-axis. And that's all you need to know about that. So let us first consider, are there any questions? It's 3 rules. Okay. Then, let us start analyzing. There are things you have to know to analyze. You need to know the x and the y intercepts. You need to know the asymptotes. And it helps to have a graphing calculator. And you have to know if you have any points of discontinuity, which are colloquially called holes. So we are going to analyze this. right now. And the way I start is this. I always find the domain first. And to do that, I have to factor. The denominator is going to be factored by the difference of two squares. Now don't cancel yet. You can see that x plus 1 and x plus 1 match. They're going to cancel, but not yet. Because we have to find the domain, and that's a separate question. I set each factor equal to 0. I subtract 1 from both sides. 1 minus 1 is 0. So I'll have x on the left and negative 1 on the right. And then over here, I'll add 1 to both sides. Negative 1 plus 1 is 0. So I'm left with an x on the left, and I'll have a positive 1 on the right. These are the two numbers that x is not allowed to equal. Whether there's any cancellation or not, the fact is, if you come to the original function and you plug a negative 1 in for x squared, you're going to get 1 minus 1 is 0 on the bottom, which will be terrible. And the same thing for if you put a 1 in there, it'll be 1 minus 1 is 0. So, our domain, I already wrote it over there. Don't need to write it again. The domain is going to be, if you write it in set builder notation, all x such that x does not equal negative 1 and x does not equal 1. And in set up interval notation, negative infinity to negative 1, unioned up with the right side of negative 1, going all the way to the left side of positive 1. It's easier if you draw a picture. Unioned up with the right side of 1 going all the way to positive infinity. And indeed, if this is the x-axis or the number line, we have negative 1, we have 1. Those are taken out of the x-axis, off the x-axis. And so all of the numbers from here to here are going to be okay. And all of the numbers on the x-axis from here to here are going to be okay. And all of the numbers on the x-axis from here to here are going to be okay. And you put a U in the middle. So I have to think about the x-axis first before I do interval notation, since there's a relationship there. Okay, now I know for sure what the two numbers are that cannot be used, period. Now I find the vertical asymptotes. This is where you have to be careful, because if you do have cancellation, then you're going to lose a vertical asymptote. Doggone it. Well, let's see. So, vertical asymptotes. I should write not just vertical, but vertical asymptotes. Okay, we factored. We have x plus 1 over x plus 1 times x minus 1. And the x plus 1 and x plus 1 cancel. Before I cancel, I want to point out to you that x plus 1 gave me x equals -1 as one of the points that cannot be used. So this gave me x cannot be equal to -1. It's going to go bye-bye. X plus 1 goes into x plus 1 time. That's how you're going to get a 1 on top. This is what you're going to be left with. Okay? Now, there's no way that you are going to get rid of this denominator. No more cancellation. You're stuck with it. If x minus 1 equals 0, you are in deep doo-doo. Especially if you work at a power plant, because something's going to be exploding. That's really true. This right here is the equation of the only vertical asymptote you have. This is the equation of vertical asymptote. Va. Well, what the heck about this? We still can't use -1. It's just not a vertical asymptote. It's just a number we cannot use for x. And thus comes our next category in our analysis of this vertical, of this rational function. Okay, holes. The quick and easy name for points of discontinuity. When you lose a vertical asymptote because factors cancel, what happens is you're going to get a hole in the graph. Hole in graph, which we haven't done yet. A hole in the graph at x equals 0. Well, we can now find out what that point is because we have what f of x equals now. So we have to use the new version of f of x after the cancellation, otherwise you would end up with a 0 in the denominator. So you're left with 1 over x minus 1. If you let x equal 0, you'll have f of 0 equals 1 over 0 minus 1, which is 1 over -1, which is -1. Therefore, your whole is going to be the point. See, whole is the point. X equals 0, y equals -1. So now you've got a vertical asymptote and you've got a whole once we get around to drawing the graph. We don't know enough yet to write an accurate graph. That's on its way. Now we're going to find the intercepts, the x-intercepts and the y-intercepts. For this, I have to use the new version after cancellation. So let's find the x-intercepts or x-intercept. If there is one, and there's no rule that says there has to be one, like right here, there is not going to be. We now have f of x equals 1 over x minus 1. The method for finding the x-intercepts is this. To find the x-intercepts, set the numerator, the top, equal to 0, and solve for x. There's no x. There's no x in my numerator. I can't solve for x. Oh dear. That means I don't have any x-intercepts. That means that the graph will not be crossing the x-axis. No x-intercepts. Okay. Okay, it happens a lot. Whenever you have just a number on the top, you are not going to have any x-intercepts because there's no x. Okay, now the y-intercept. The y-intercept is where the graph crosses the y-axis. So you've got f of x equals 1 over x minus 1. The y-intercept is f of 0. And that's one of the things that's always going to be true. Let your x's equal 0, you get the y-intercept. So f of 0 is going to be 1 over 0 minus 1, which is 1 over -1, which is -1. But oops! Oh yeah, we can use 0. We can let x equal 0. Okay, I hate it when I get things wrong. Let's go back to the holes. I said the hole in the graph at x equals 0. It was x equals 0 yesterday, not today. Duh. It's at x equals -1. Okay, so if x equals -1, and that doesn't look like much of an equals, the hole in the graph at x equals -1. Okay, now I have f of x equals 1 over x minus 1. If I let x equal -1, I'll have f of -1 equals 1 over -1 minus 1, which is 1 over -2, which is -1/2.
Miss Barbara.
Wait. I want to finish this. So
Okay.
my point of discontinuity is going to be located at x equals -1, and when x is -1, y is -1/2. This is my point of discontinuity right there. Yes.
Okay. So whenever we were finding out the vertical asymptotes, we did cancel out the x plus 1 and x plus 1, right? And we decided that that was going to be a whole.
Correct.
Okay. And so then to find the whole, you just substitute what the x would be in for the equation.
Right, the x that you got from the factor that you canceled.
What if you don't get any holes in the vertical
Oh,
asymptote?
a lot of the time you don't get any holes. You don't have to get any holes.
Okay, so
Like in the first one, we didn't get any holes. Oh, we haven't done one. This is the first one. You are not going to always have holes. In fact, most of the time you will not have holes. This
okay.
is just in case you do.
And so what else? I think that's it. Yep. Or okay. Another part is, what if, is that the order that we're supposed to solve this in?
No,
So
analyze it. No, you can make up your own order. They'll be asking you things. But like, for instance, it says, all this says is list the domain and the x and y intercepts of the following function.
right.
Graph the function. Be sure to label the asymptotes. That
Okay.
means you've got to find the asymptotes. So x-axis, y-axis, vertical asymptotes, horizontal asymptotes, holes, and anything else that might be of interest.
Okay. Mm, okay, those are all my questions.
Okay, great. Feel free to pop in with another one. Thank you. I knew that we couldn't use 0. Of course we can't. That should have been x equals -1. Again, okay, the holes are going to be where x equals -1, and there's only one. So the hole is going to be where x equals -1. So I put that in the new version of f of x to find out what the y coordinate would be if x is -1, and I got -1/2, and that is the hole. Now, and when you graph it, you put a little empty hole at that point in the graph. If you've got a hole, You're not going to have a hole if you don't have any cancellation. So you never know. Going into this, you never know until you factor whether you've got a hole or not. Okay, so now coming down to the y-intercept, there is no problem with us using 0. So the y-intercept is f of 0, which means you put a 0 in for the x, and you'll get -1. So our y-intercept is going to be the point x equals 0, y equals -1. That's where the graph, part of the graph, is going to cross the y-axis right here. There are no x-intercepts. We do have y. We do have y-intercepts. We have a y-intercept. We have one vertical asymptote located at x equals 1. I'm going to put that in right now too. Also, we haven't found the horizontal asymptote yet. So there's the vertical asymptote, and remember you have to label it, which means you put x equals 1. We would have had 1 over here at x equals -1, but it became a hole. A hole located at -1, -1/2, which is going to be right here. Okay, now. How interesting. It really is. Okay, now we are going to find the horizontal asymptote. And you can go back to the original for that, or you can use the new version, the horizontal asymptote, the HA. Again, if it's got one. Let me get some water. Oh, my allergies are really acting up ever since yesterday afternoon. Horizontal.
Would horizontal asymptotes be a straight line or like a dashed line?
Well, it's usually dashed, but I don't have a convenient dashed line.
Will it matter whenever we need to
No.
graph it? Okay.
Not at all. Okay, so we look at f of x equals 1 over x minus 1. Or at the original, you'll get the same answer. We have a number all by itself on top with no variable. That's a constant. The degree of a constant is 0. The power on this x is an invisible 1. So the degree of the denominator is degree 1. 0 is less than 1. Therefore, your horizontal asymptote is the x-axis. And I'm going to put a blue line on that. Asymptotes are tendencies. Well, the horizontal asymptote is a tendency. The vertical line is the vertical asymptote is a definite do not cross. Okay? So now we have to figure out what this baby looks like. And that's why graphing calculators were made. Otherwise, we would have to spend a lot of time finding a whole lot of points. And I bet you have better things to do. So let's take a look. At what this looks like. Okay, clear. We go to y equals, and I can graph the original problem, or I can graph 1 over x minus 1. They'll be the same graph. I'll even show you that. 1 divided by parentheses x minus 1. Make sure that's right. Yeah, x plus 1 canceled. We're left with an x minus 1 on the bottom. Now I'm going to graph. That's what it looks like. Now, these graphs never show you, but right here at -1, where the blue line is, where the blue graph is, there is really a hole there. But it's a very, very, very small hole. We would even say infinitely small, like really small. So it's too small for the graphing calculator to pick up on. So this is what we're going to do. Now here's the hard part. Making it clear that you know. See, and I'm not. Oh. There, okay. Making it clear, even if you have to contort your body. Of course, with a piece of paper, you could just turn it. See, that's too close. It's not going to touch the vertical asymptote. And so it's really, really difficult to draw. It's great. My life in art. Let's try this again. Y'all hold your, I don't know, cross your fingers. This is probably not going to work. You can do it, I bet. Damn it. No, go backwards. I didn't say that. Did you say that? Okay, now let's just try this little bit of it. There we go. We're going to try this one more time. Maybe it would be better if I went up. Oh, that's better. Okay, now I'm going to get my white pen. and attempt to make a pseudo hole right there. Yay, that's part of it. Now the other part's going to be easier, I think. Famous last words? Okay, now that doesn't wiggle, okay? It gets closer and closer and closer, but never actually touches the vertical asymptote, or you'll have an explosion. Nobody wants that. Now, if you're wondering, well, what about our hole? What happens to it? Think about how we studied piecewise defined functions. Somebody writes a piecewise defined function so that that hole gets filled in, because it's not going to cause an explosion. A way around almost every problem. There is no way around a vertical asymptote at all, ever, unfortunately. Okay. One person has been asking questions, and she is still invited to ask more. But does anybody else have any questions? I know you do. So this isn't the end. Let us move along. Let us move along to this. And let's analyze this, or, yeah, let's analyze this. And so my order for doing it, again, does not necessarily have to be yours, as long as you get all the questions answered. But I always start with domain because that's the most important part. We're going to have x over x times x plus 7. Now you can see right now you're going to have cancellation, you're going to have a hole. But let's not jump our guns there. Right now we are only going to work on domain. And for domain, we're going to have x equals 0 and x plus 7 equals 0. And what that gives us is x equals -7. These are the two numbers that will make this denominator equal 0. So in set builder notation, we're going to have x such that x does not equal 0 and x does not equal -7. Okay, and right now, those are our problems right there. I don't want to use that though. So to write interval notation, it's a good idea to draw a quick, spiffy little x-axis. And you'll have -7 somewhere over here and 0 somewhere over here. So you take those out. And then all these numbers are going to be okay. And all these numbers are going to be okay. And all these numbers are going to be okay. And then you put a U in between them. But this helps you write -infinity to -1, the left side of -1. And the right side, yeah, the right side of -1, all the way to 7. That's 7. I've just declared that -7. All right. Love it. Go back to blue. The left side of 0. Come on, we can make that better. More 70. More 70. Yeah. And then from the right side of 0 to infinity. And then a U in between. And you'll find the right U to use. It's not just a capital U on your keyboard, it's more rounded than that. And that will be in the toolbox in my math lab when you need it. You know, every time you click on an answer box, the toolbar appears underneath, you know, at the bottom of the screen. So you've got every tool you need there. If you don't see it, click on more. You'll see a whole bunch of symbols. Probably everything you would need. Okay. So either way, depending on what the problem is asking, how it wants domain. And here's George, right on cue. This is set builder notation. And this is interval notation. Interval. Okay. Now, we took care of the domain. And the next question, I mean, you can't decide on what your vertical asymptotes are until you know the domain. So, vertical asymptotes, VA. We've got x over x times x plus 7. And this gave us x equals 0. And this gave us x equals -7. Well, I've got to cancel. Boom. And I'm left with 1 over x plus 7. So now our function is going to be f of x equals 1 over x plus 7. All right, now we're stuck with x plus 7. So that'll give us x equals -7. This is going to be our only vertical asymptote. And this is going to give us our whole. And that really is 0. We're not going to be able to use x equals 0. We are going to have a whole there. So, okay, your vertical asymptote is, the equation of the vertical asymptote is x equals -7. Now that we know we have a whole, let's say where the whole is. The whole is at . And the way to find out what the actual number is, the actual numbers in parentheses to make it a point, because it will be a point, is to come over here to our new f of x equals 1 over x plus 7. And take out the x's and put in a 0. Take out the x, put in a 0. So I'll take the x out, and I'll take the x out. And I will put in a different color 0. How about that? So that will give me f of 0 equals 1/7. That's where the whole is going to be, where x is 0 And the y coordinate is going to be 1/7. 0, 1/7 is our whole. Again, right, it looks like this one is, since it's not negative, it's right above, a little bitty bit above the x-axis. Okay, now, the intercepts, again, the x-intercept is going to be a total washout because I have just a number on the top, see x-intercept. The x-intercept, well, what would I do? I would take the numerator, set it equal to 0, solve for x. But there's no x. But no x. That means no x-intercept. Does that happen all the time? No. Often you have one or even two x-intercepts. The y-intercept. Well, now that's going to be a problem. The y-intercept occurs where x is 0. And what can x not equal? Yeah, the y-intercept, the y-intercept occurs where x equals 0. But x cannot equal 0. In this problem. What do we do? It means we're not going to have a y-intercept either. Is that legal? Yeah. Where would our hole have been if we could have? Yeah, okay, so at 0, 1/7, that's where our hole would be if we could use 0. And here, that's precisely how we would find the y-intercept. F of 0. If I could use 0, my y-intercept would be, but I can't, so instead I'll have an open hole. Okay. Now what? Now what? Now what? Horizontal asymptote. Okay. We're going to have the same situation we had before. Whether you use this or whether you use this, the degree of the bottom is higher than the degree of the top. The degree of the top is 0. The degree of the bottom is 1. So, our horizontal asymptote yes, it is, which is the x-axis. except, no, never mind that. X cannot equal 0. So we are going to have a little problem there. But we'll worry about that when we come to it. Okay, so now we have the information we need. We have a vertical asymptote at X equals, at X equals -7. So let's put that in first. Here's -7. And we're going to have a hole at what would have been the Y intercept, which is 0, 1/7. No, I need to use that. Not because color is important, but because it's the only really skinny marker I've got. It's actually much closer, but I can't draw it closer. Okay. Now what else can I actually, I'm going to have a hole, that's also the Y-intercept. There are no X-intercepts. All right, and the ha is Y equals 0. Except not where X equals 0, so I'm going to have to come back and take care of that. Okay. All right, now I'm going to look at the graph. Oh, check this out. Okay. All right. 1 over X plus 7 graph. It's the same basic thing.
On my calculator, I'm sorry, but my calculator, you can actually see the whole.
No! That is great. What kind of calculator do you have?
A TI-84 plus CE.
That's what this is supposed to be. Well, darn, I envy you. This is X plus 7. X plus 7. I just thought I'd do it again to make sure. One, 2, 3, 4, 5, 6, 7. Okay. All right. So here we go. Nothing terribly creative this time. Most of them aren't until they get really complicated, but there's no reason for you to do that. So this is way out here, really, really close to the x-axis, but underneath it, not crossing it, because we proved we don't have any x-intercepts. Not touching, that's an illusion. Okay, now. And there's our graph. Probably should be down more. Should have found maybe a point in here, but I didn't. Looking at the time to see if we have time for one more, but we really don't. So go home and play with this. It gives you a chance to actually be creative. Okay? Or hang around and talk and ask questions.
Have a nice day.
You too. But I'll be here for a while.